Now, in this last section, I want to show you what traces of life we find in these ancient sediments. This is what you want to hear. I've made you wait a whole lecture, giving you all the background detail, but now you understand the environment, you understand how the signatures are preserved, what we have to do to try to identify them, study them. And so let's go for it. Again, I just repeat, we only have 2 areas in the world where these signatures are preserved. So we just, I'm going to show you examples from Australia, from the Pilbara region, and an example from Barberton in South Africa. And what kinds of signatures do we find in these rocks? Well, we find signatures of chemolithotrophic organisms. These are organisms that have the most primitive types of metabolism. They're organisms that obtain their energy from carbon, from minerals, from gases such as hydrogen. Their carbon source is either from carbon, again, sorry, Frenchism there, carbon or carbon dioxide. But then we also see evidence for phototrophs. As I mentioned before, phototrophs have a more evolved metabolism. They probably appeared on Earth later than the chemotrophs. They obtain their energy from light. They form biofilms and mats, stromatolites, these 3-dimensional structures, and they can also be found in the planktonic, in the water column, in the upper layers of the water column. They need light, so they form only where there is sufficient light. And these are the main organisms. Now, I'm going to start off. Phototrophs are easier to identify because they form physical structures that are difficult to mix up with something that's abiological. So I'll start with the easy things first, and then we'll go on to the difficult things. Again, the strategy, always, you go to the field. You go to the field, you look at your geological environment, you study the rocks, you take a specific rock from a specific environment because you think this might be an environment where there might be traces of life, if that's what your aim is for. You decrease you increase the magnitude of observation. You look at things microscopically with the various electron microscope, various types of microscopes. You look for morphological features. You can look for colony features. Going down to the molecular level, you can look at the bioorganochemistry, biogeochemistry, up to isotopic fractionation. So you use all of these. And I'm going to insist on the importance of field context, because when I first arrived in France, I was talking to I won't mention any names, but I was talking to a famous geochemist. And I said, I have some very nice samples from the early Earth that are well characterized. I know exactly where these samples come from. And he said to me, "Oh, that's fine. I don't need your samples. I have samples that somebody else sent to me." And these samples that somebody else had sent to him had not been properly characterized. And he said to me, "You geologists, you can do the field work. We don't need to do that." Those were the implications of his words. "We don't need to do that. We do the real work. We do the geochemistry." Well, he made some mistakes in his interpretation. Okay, so this is really important, and it's not just because I love going into the mountains that I do this. You have to believe me. So we have the environment. Again, another Frenchism. Oh dear, sorry. Anyway, we have our environment. We're in a shallow water environment, coastal environment, volcanic sediments, hydrothermal influence, just to remind you, in case I hadn't really brainwashed you with this. So let's have a look firstly at the evidence for phototrophic life. So the environments where phototrophs could form, they can form in the beach environment where there's light and water. They can form in the ocean column eventually. They can live in the ocean column close to the surface where the light penetrates. They can form on the surfaces of the sediments or even volcanic rocks if they're in the light zone. And they can form also around the hydrothermal vents if it's in the right environment. The only criteria is they need light. They need light. So this is there's quite a variety of environments where they could potentially exist, and in fact we do find them there. Again, to put you into the scene, lovely view of mud flats. I think this is in North Germany, actually, mud flats. And if you, as I mentioned, if I showed you, if you take a spade and you go through the mud flats, you can see different layers. But in this case, if you take a spade and cut through the mud flats, you can find layers that correspond to layers of mats, microbial mats that are formed by phototrophic microorganisms, all the layers that are sticking out. This is work done by Gisela Gerders in the 1980s in Wilhelmshaven. And she studied the microbial mat formation in this kind of environment. And we will also see something similar from the early Archean. So you can see these layers, very, very striking layers formed by the sticky microbial mats. And if you increase the magnification looking at these microbial mats, you can see that they start getting filamentous, and they form a sort of wispy, wavy, up and down type of structure. This also can get preserved, and I'll show you some examples. So this is just to set the scene. Now, this is a thin section of a rock from Barberton. We have a thin section of the chert that I showed you from Barberton, the Joseph-style formation. And it's what we see here is a sort of dark layer that's quite dark, spotted dark, and also a bit of current controlled sedimentation here, some ripple mark, very fine sediments. But what I want you to have a look at is this dark horizon here. There's a definite horizon. And if we zoom in on that horizon, we see that it's coated with a very fine, filmy layer that's formed of different packets of very thin films. The scale bar for is 200 microns. These films are about 10 microns in thickness. They're very thin, but just look at them. They're very thin, wispy, wavy. They coat the underlying bed forms. They're not completely parallel. They include various other objects that are trapped in them, and they're very similar to these bed forms, these microbial mats that we see on modern sediments in the photic zone today. Now, these can be seen in thin section. They obviously formed on a sediment surface, and they were coated by more sediments. So we know that they're in situ. As I mentioned, syngenicity is important. Now, from the same rock exposure in another sample, I found on the surface of the rock, the surface coated with this kind of filmy substance, which has a definite orientation. And in fact, there are different layers of these filmy substrates. There also seems to be curling up. And in actual fact, what we're looking at here is one of those microbial mats, photosynthetic microbial mats, that was desiccated and exposed to the atmosphere. I'll show you evidence for desiccation. And it's formed of very fine filaments. If you look at looking at the scanning at this structure with the scanning electron microscope, we can see definite filaments that have the same width and and are quite extensive. They're less than half a micron in thickness, and they're thickly encased in kind of film mucus-like substance. And all of this is silicified, but there's organic carbon in it, and I'll show you the organic carbon later. So this film is formed by filaments, as in modern photosynthetic mats. They're associated with very thick layers of of mucus, of polymer, as in modern photosynthetic mats. Remember I showed you the modern photosynthetic mat from Shark Bay? Well, this one also has cracks in it. There's even soft deformation, tearing as it's drying out. These are features that cannot be formed by something that's already lithified. It was still soft. This is soft deformation, plastic deformation. So these mats were periodically exposed to the atmosphere. And not only that, but we get a suite of evaporite minerals. These are pseudo-evaporite minerals because they've been silicified, but we get a suite of evaporite minerals that are embedded in the surface at the different layers of this mat. And the evaporite minerals include pseudomorph gypsum, aragonite, halite, and high magnesium calcite. And they're embedded. You can see, I think here you can see a filament overlying one of the grains, and here as well, and in other layers you can see different layers. So we're definitely in, we know we're in, apart from the sedimentological features, we know we're in a very shallow environment, possibly a beach environment. Now, because we have such a well-preserved, relatively large structure, this feature covers covered about 6 square millimeters on a sediment surface where it was exposed. We can actually do some detailed work on this. And I'm going to go into some detail to show you the kinds of analyses that we can do to look at the different kinds of biosignatures associated with this feature. Because this is what we can do in a laboratory here on Earth. Think about trying to do something like that in situ robotically on Mars later on. You'll see it won't be possible. Anyway, so one way of, there are a number of ways of studying this feature in more detail, because it would be interesting. We're lucky to have such a well-preserved structure. We can dig into it, have a look at its vertical section, do mini stratigraphy on it, compare it to modern microbial photosynthetic mats. We can take slices out of it as ultra thin sections for observation with the transmission electron microscope, for observation with the scanning electron microscope, synchrotron, nanosims analyses. We can do all of these things to document the biosignatures. So first of all, let's have a look at the morphology of this feature. So we're looking here at this wall. The scale bar here is 10 microns. So we're looking at this wall here. First of all, artifacts. All this pitting on the surface is because the way to cut into this material, we're looking at material that's silicified. So we use a gallium beam to sputter, to cut slices through the rock, and it leaves pits. So these are artifacts. But you'll notice that there's a surface coat of a light greyish colour. The scale bar there is 5 microns. So it's possibly 200 nanometers or so thick, underlain by sort of slightly darker grey layer, and then the bottom is sort of granular. But you'll notice also that there are these spikes cutting into the bottom. What are they? The matrix, the matrix of all of this is silica. Everything's been silicified, recrystallized to microcrystalline quartz. What we're seeing here is the quartz matrix, and these are the quartz crystals that are cutting into, as they recrystallize, they actually disturbed the base of this feature. So they're cutting into it. So we know, that this feature formed before the silicification and the metamorphism. More details. We take a slice of this material, and at the top of the slice we find these pseudomorphed evaporite minerals. In fact, this is gypsum. We notice a portion of the silica coat, and here in this particular case where we took a slice out of the structure, because of the drying it had lifted up from the base, and silica had coated the underpart of the structure. The very dark grey areas are almost pure kerogen, and they're two locations, mostly the top of the feature and a little bit down here. This is pure kerogen, and in actual fact, keep in mind with photosynthetic microbial mats, they are stratified structures. The top layer it consists of the active organisms. These are the active photosynthesizers. They're the ones that are creating the biomass. Underneath, where you have the photosynthesizer, you have the dead organic matter from the photosynthesizers. You have the heterotrophs. They are living off. They are oxidizing the organic matter. This is what they're living off. So these features are very stratified on a micron scale level. So we have the top layer of kerogen here, and you'll notice that the bulk of this feature is sort of light grey granular, and it's actually carbonate. It's aragonite, and I'll go into more details there. And finally, right in the middle, there are some tiny grains, floating grains of quartz. Remember, these features are sticky. We're looking at polymer, which is sticky, and detrital grains stick to it and are entrapped by them. So we can study, in fact, what's happening here, and I'll show you the details in the next few slides, is that this top layer of pure kerogen that hasn't been calcified represents what was the original layer of living organisms. The lower layer, which has been replaced by granular calcium carbonate, represents the layer of degraded organic matter that has been remineralized. It's been oxidized by the heterotrophs and most likely sulfate-reducing bacteria. I'll show the evidence for that in the next few slides. And it's the metabolic. It's the effect of the metabolic activity of the sulfate-reducing bacteria that has created in situ calcification. All of this has then been silicified. It's impregnated with silica as well. Anyway, so this is the sequence of events. Now, in terms of analyzing the molecular composition of the organic matter, there are a number of methods that we can use. In this particular slide, I'm showing just one of the methods. It's micro X-ray adsorption near-edge spectroscopy, in which we've been looking specifically at the sulfur content of this carbon-rich layer. With the SEM, we can map the carbon, but here we wanted to look at exactly what are the kinds of molecules that we can still detect in this matter. And in fact, the kinds of molecules that we can detect are heterocyclic molecules, i.e. extremely degraded organic molecules. This tells us that this material is very old. It's already and also the Raman spectrum signature says this organic matter has the same maturity and age as the rock in which it's found, another indication for syngenicity. But we find the molecule thiophene. This is a sulfur-containing molecule. And this molecule indicates that the organic matter here, the kerogen, the degraded organics, have been enriched in sulfur. They've got more sulfur than in the living organisms, and the enrichment in sulfur is due again to the activity of the heterotrophs, the sulfate-reducing bacteria, liberating the sulfur, and it's being concentrated in this area. We can also have a look at inorganic sulfur in the form of sulfate, and there is a little bit of sulfate associated with carbonates here. Again, another indication that we're probably dealing with the activity of sulfate-reducing bacteria. And I'll note here Laurence Lemel, Alex Simiovici, the ESRF in Grenoble. These are people with whom I've done this work. I've also used TOF SIMS on this material. Now, Hervé spoke about TOF SIMS yesterday with respect to the Rosetta mission. And the TOF SIMS, I haven't, again, because of my computer problems, I wasn't able to insert the slide. But the TOF SIMS of these samples indicate again that the organic molecules that are in this rock, associated with the organic matter in this rock, are basically polyaromatic hydrocarbons, PAHs. These are very degraded molecules. And they are, just like thiophene, these are molecules that are found in abartic organic matter in meteorites. However, there's a difference in terms of the distribution. Abartic organic matter in meteorites has a very, very broad molecular distribution. And in the Tough-Sims analysis of the organic matter of this particular rock, the molecular distribution is rather restricted, which is more similar to organic matter issued from biological materials. However, this underlies the difficulties of dealing with very old material. And remember, this is on Earth with top-level sophisticated equipment. And later think, how the hell are we doing this on Mars? Okay, so we're going to have a look at the calcified part of this feature, this mat-like feature. And in actual fact, I mentioned that it's very granular, and this is a TEM TEM photo from that granular structure. You can see it's got a sort of network. There's a lot of carbon still in it, but it's got a kind of network texture, which is typical for degraded organic matter. But if you look very closely, this is work I've done with Barbara Cavalazzi and Caroline Andreazzi in Orléans when Barbara's there. We can actually detect why this material is so granular. We can find nanocrystals of carbonate. In fact, it's aragonite. They're very small. They're 3 to 10 microns in thickness. And they are embedded in this kerogenous material. And this is very interesting because, in actual fact, aragonite is not a stable mineral under general atmospheric conditions, and it transforms naturally into calcite. Here we're looking at a feature that's 3.3 billion years old, but there's still aragonite there. And the reason for that is that everything was almost immediately silicified, permeated with silica, which froze every single thing in time. This is why the features that we can see in these rocks are so beautifully preserved. It was the silica. Although I can also say the silica is very troublesome too, because if you're looking at geochemical signatures, for instance, what you would normally be a trace of trace quantities of elements in a feature become traces of traces of traces, because we're looking at 99% silica. Anyway, so with this slide, I just want to underline the reason for the calcification due to the activity of sulfate reducers, changing the physicochemical conditions within the degrading mat and contributing to the calcification of the feature before its silicification. So there we have evidence of bioprecipitation. So there are quite a lot of signatures, potential signatures that can be studied. What about carbon isotopes? Well, if we take the whole rock, we grind it up, we get a general measurement of about minus 22, 23 per mil. Taking just the dark layers that are carbon rich, it becomes almost minus 27 per mil. But then if we do in situ measurements, and we've been doing this in Nancy, we get quite a wide range of signatures. But all of these signatures are compatible with the fractionation of carbon by microbial processes. As I mentioned before, meteoritic carbon also has this kind of fractionation, but the signatures of fractionated carbon in meteoritic material are far wider, far broader. In material of biological origin, the signatures are much less, as we see here. So, what about the physical structures? I've shown you a feature that was very small, very fine. But there are also larger structures that have been interpreted as evidence of phototrophs in the early Archean, and features similar to stromatolites but a lot smaller. Again, stromatolites today are produced by by mats that are primarily produced by oxygenic cyanobacteria, but again are mixtures of other kinds of microorganisms. And in the early Archean, we also have features that are similar to microbial mats. In fact, I'll go to the next one first. In this image from the Strelley Pool Bay in Australia, the rocks are about 3.45 billion years old. And you can see the sort of typical domical features. There's been a very nice study on these done by Abigail Allwood and some other people as well. And these features have a typical shape of stromatolites, but they're a lot smaller. I mean, here's the hammer for scale bar, whereas the modern ones are about 1 meter in size that I showed you from Shark Bay. These are about 10 centimeters in size, and you can see them in plan view and in section here. And when I was there in 2000 in this particular region, I found a nice example of a squashed stromatolite. There was a hydrothermal vein just to the right of this feature, but you can still see the layering, the fine laminations, and there was obviously a precipitation. This is hydrothermal silica. There was a precipitation of hydrothermal silica on top that just squashed it. Remember, these are gelatinous features. They're not solid, they're gelatinous, and they're easily squashable. So that's a nice example of a squashed ancient stromatolite. There are also there have been a number of studies recently on certain features that are found in these rocks that are a lot larger than the features that I have shown you and that I will show you in the next section on the chemotrophs. You can see the size scale bars here. They're about 50 microns in size, the scale bars are 50 microns, and these features can be up to 100 microns or so. But they're very large. They look like spindles. They seem to be hollow. Sometimes they're filled with balls. And it's been mostly Ken Tsuchitani with other colleagues who've been working on these features. And they are found associated with the volcanic sediments, the silicified volcanic sediments, and I think are interpreted possibly as planktonic organisms. They're a lot bigger. If they're planktonic organisms, then they had to have been phototrophic, the only way that they could survive. I think there's still work to be done about the interpretation of these features, but for completeness, I like to tell you what is being done at the moment. Also, in rocks that are slightly younger than the ones that I'm showing you, 3.2 billion years old from Barberton in the Fig Tree Formation, Emmanuel Javot's done some very nice work on flattened organic cellular-like features found in very fine-grained volcanic sediments. Again, what are they? We don't know. Possibly floating phototrophic cells, because these are large. They can be up to 200 microns in size. They're very, very big. So there seems to be a diversity of phototrophs already in these very ancient rocks. Now, I wanted to show you the relatively easy things first, just to underline the difficulty of trying to study the traces of chemotrophic life, because the chemotrophs, they don't form big mats. They don't form recognizable mats. They do leave features that are perhaps more. They're not quite so evident, and I'm working on these particular features at the moment. I will give you the state of play. I cannot say that I have you can make your own interpretations as to the evidence. There's obviously a lot more work that needs to be done and will be done primarily by Kieron on these features in the future. But I think it shows the at the same time as giving you an idea of the diversity, the preservation of potentially biogenic features in these ancient rocks. It also underlines the difficulty of these kinds of studies. So now we're going to go to the Pilbara. Again, we're looking at sediments that were deposited in the coastal area. You can see a little bit of cross-bedding, flazer bedding here. We're going to look at a sample, this particular rock here, this portion, that's where the samples come from. As a marker horizon, you can take this layer with the spots on the top of it. The spots are actually pieces of pumice, fragments of pumice that have been sedimented on the top. In fact, what we're looking at in terms of environment, we're looking at a tidal channel that's being infilled. So we have sort of sediments, volcanic sediments that are have been reworked by currents down here, and the top where it's very flat lying, again we have again sediments that are ashfall that's just depositing in the sediment and forming flat layers. So again, to underline the similarity, the cross-bedding and so on, we have, I'm going to start well at the bottom. You can see sort of a slight channel here. There's a little channel formation. This light cream-coloured layer indicates that there's been some subaerial alteration or a stable sediment surface at this particular place in time. But then there's been infiltration of hydrothermal fluids in the lithified sediments. It's broken through but parallel to the layers, again parallel to the layers. We have nice ripple marks, preserved ripple marks in this particular layer. This is the layer that was probably exposed to the air, with the pumice stones just sort of they float on the water, but when the water disappears, they just plop on the sediment, slightly embedded in the sediment. And this dark layer here is very fine-grained volcanic ash, very rich in organic matter. And these flat-lying layers are just layers of volcanic ash that's deposited. So in terms of environments for microorganisms, we're talking about microorganisms that don't care about light. So they can live in the interstices, in this water-impregnated sediments. They can live on the surfaces of the volcanic grains. They can live in the pore spaces. Phototrophs, for instance, can form on the surfaces of stable bedding planes. The chemotrophs, who don't need light, can live. Pumice is very, very porous. They can live in the pores of the pumice. So there are a number of volcanic environments, microenvironments for microorganisms. If you take a thin section of this particular rock, this is a typical thin section from this rock. You can see angular particles. They're about of the order of 50 to 200 microns in size. This is typical angular particles. You notice that they have dark borders. Now the dark borders are due to two things. Here we're looking at a Raman spectrum of the surface of a thin section, of that particular thin section. We're looking at this feature here, which happens to be a portion, a fragment of glass, volcanic glass, a glass shard. And the dark layer around it is due to the presence of carbon here in green, coating the surface, carbon, and also to the presence of anatase. Anatase is titanium dioxide, and it's a typical phenomenon of the alteration of volcanic particles in seawater. It's everywhere. Every single volcanic particle has titanium oxide on it. Every single volcanic particle that's been altered. But there's another interesting feature here that gives us some information about not just the anatase, but also the alteration of these volcanic particles Remember, we're looking at ocean water that's slightly acidic, that's warm. I should have mentioned just a couple of meters away from this particular exposure, there is a big hydrothermal vein coming in that brings in silica. We can see the outline of the grain here, but in the middle, the pink color is muscovite. Now, muscovite is a metamorphic product of the clay. Clay is the alteration product of the original volcanic particle. So everything was being altered. All the processes were going very quickly because we're in an acidic environment and it's hot, so processes are quick. So this is the background, but note the presence of carbon. Why should carbon be around these grains? Well, related to this phenomenon, this is a scanning electron backscatter view of a thin section surface. These are the volcanic particles in light grey. The quartz is in the slightly darker grey colour. And you notice that there are sort of tunnel features at the edges of these particles. And these tunnel features, they stop at the edge of the particles, but they're filled with this kind of filmy substance, when in actual fact it's silicified kerogen. It's carbonaceous, and this is an atomic force microscope scan of this particular part of the filament, this organic matter that's coming out. So why would you have a tunnel filled with carbon in these rocks? And before I answer that, let me show you some other images that we've taken from these volcanic particles. This is a scanning electron microscope image of the edge of a volcanic particle. You can see these sort of layered, flaky minerals up on the upper left. These are the phyllosilicates that have altered the volcanic particle. There's a quartz crystal here. This is the quartz matrix. But just at the border, there's a kind of carpet of beads. This carpet of beads is carbon-rich. Now, if we look at the carpet of beads a bit more closely, you can see that they have particular features. They seem to be dividing. There seems to be two class sizes, smaller one about half a micron in size, larger one about a micron in size, and they're coated with a film. So our interpretation of these tunnels and these carpets of beads are that these volcanic grains were colonized by chemotrophic organisms, specifically chemolithotrophic organisms that they love the volcanic grains because they can get their energy from redox reactions at the surfaces, and they can get their essential nutrients, the transition metals, from corrosion of the features. So what we're seeing here are tunnels corroded into the surface of the volcanic grains by the presence of colonies of organisms that have colonized the surface of the organisms. Now, I want to show you some details of these structures because I spoke about the superb preservation of this material, and it is superbly preserved. Okay, remember what in fact, I will repeat here, what I'm showing you is probably only a portion of what was there, because only a small portion gets preserved. Anyway, so there are some magnificent details preserved in these features. The beads I'm interpreting as microorganisms, colloidal microorganisms. But just look at the details here. In this particular structure, you can see cell division and even a meniscus where the dividing cells are pulling away from each other. In this particular photograph, you can see again two sizes, a larger one, a smaller one, again with cell division. But there's something special about this particular photograph, and that is that you notice whereas most of the cells seem to be turgid, they're full, they were living when they were silicified. This part is deflated. So we're probably looking at a cell that had lysed and was deflated. So in the same photograph, in a rock that's 3.46 billion years old, we have life, cell division, and we have death, lysis, beautifully preserved. I'm showing you the best of the best, my jewels. I won't tell you how many hours of patient searching and not seeing anything. That's boring. So what you're seeing is the best of the best. Some more images from this particular sample. Again, cell division. However, here we have a situation where the organisms were apparently dead when they were fossilized, because we seem to have a chain of coccoidal cells. All of these features contain carbon. We have a chain of coccoidal cells, but they're deflated. They're not turgid. So they were obviously dead. So depending on different layers, different ages of colonies, there's different types of preservation states of the organisms. Now, these ones we have morphological features and the presence of carbon. I only have bulk isotopic compositions for different layers, which are consistent with fractionation by microorganisms. I do not have any detailed work yet on the nature of the organic matter, and this is what Kaon is going to do. So now I'm going to show you stuff that's a little bit more difficult to interpret. Again, we have our thin section that I showed before, where we had evidence for phototrophic microbial matter at the surface. This rock, this thin section, comes from a chert. It's like the other cherts. It's black, and it's full of silica, but it's different in the sense that this particular one, it's matte black. It's not translucent black. This one has a much higher organic carbon content than the other cherts. And if you have a look at the black layer, you can see it's got a kind of spotted texture, mottled texture. And if you saw that in a modern sediment, people would automatically think about they would call it a thrombolytic texture, in the sense that of colonies, microbial colonies, leaving spots. Now, we're in the early Archean, so we can't say that yet. But all of the black, it is carbon. There's a lot of carbon here. And if you look at these spots more closely, you can actually see that they are coating volcanic grains, thickly coating volcanic grains. In terms, I say thickly, but the coatings can be up to about 25 microns thickness. That's a lot. So they're thickly coating volcanic grains. We can see, I don't know if you're able to see a little portion of a volcanic grain jutting out here. With the Raman, we can map the anatase here. We know that anatase is the alteration product of the volcanic grains. So we know that we have this concentration of carbon is on top of a volcanic particle, and there's a lot of carbon in that sample. As I said, all the black matter is carbon. We think that these spots of carbon on the volcanic particles represent microbial colonies. Now, but they're different to the ones I showed you from the Pilbara, because these volcanic particles are thickly coated with carbon. Why would there be such a difference? And the difference is that there's a hydrothermal vein coming into this particular sediment layer. It's bringing in a lot of nutrients. It's bringing hydrogen. The chemotrophs is bringing a lot of nutrients for chemotrophic microorganisms. And in fact, only in this layer do we have a really thick concentration of what we think are chemotrophic organisms. So in this case, the development of the chemotrophic organisms is controlled by the distribution of hydrothermal fluids. And in actual fact, in a recent evaluation of preferred landing sites for looking for life on Mars, hydrothermal systems comes out top. So, in the recognition of the importance of hydrothermal fluids in bringing in nutrients for chemotrophic life forms, very simple life forms. So, but we haven't gone any further with this material yet, and more work needs to be done. So anyway, so probably in the next years you will hear an update on this material. Now I want to speak about other intriguing remains that have been found in these ancient rocks. Again, still staying in the Barberton Greenstone belt, in the Moody's group, which is young, it's 3.2 billion years old. I mentioned that in the sandstones, in the beach sediments that have been silicified, there are cracks in the rocks in the upper left. And Christoph Heubeck's group and his PhD student Horman have been studying these cracks, and they found stromatolite features, but inverted stromatolite features at the tops of these cracks. Such features can only form in the air. We're talking about stalactites, in fact, stalactites that have a structure that's exactly like an inverted stromatolite. And the dark layers are richer in carbon than the lighter layers. And in these dark layers, Christoph Heubeck's group have found they found molds of features, molds of rod-shaped molds with septa, which look very similar to chains of rod-shaped microorganisms. And the scale bar there, 1 micron here. So these are quite big features. And they've interpreted this as, these features as being formed 3.2 billion years ago in a crack in a rock that's exposed to the air. So there seems to be these are the oldest rocks that we have, the oldest rocks we can use, but there's quite a variety of forms of life already that have been interpreted from these rocks. What about viruses? Viruses, well, it's believed that viruses were around at that particular time, just as prokaryotes were around. Would we be able to identify them? Well, with my former PhD student, François Orange, we actually fossilized viruses. You can see that the small sizes, the scale bar is 100 nanometers, 200 nanometers. And on the right are the fossilized versions of the rod-shaped and the lemon-shaped features, viruses that you see on the left. There is no way, if I saw structures like that, there is no way that I could interpret them as being originally living organisms. Well, if you think of viruses as living organisms. Just to give you an idea, again, imagine these are your volcanic grains. They're sedimented, they're fossilized, and this is from the Pilbara sample. You put the viruses in this particular material, and this is scale to scale, so they're so small. You could see them, but you couldn't identify them. Anyway, so they're even difficult to identify in the laboratory. So to conclude this section on what we early life on Earth, we have traces of chemotrophic life. We have traces of phototrophic organisms. But one of the characteristics of these biosignatures is, apart from the stromatolites, if we're looking at cells and colony features, they're very small. The organisms, the individual organisms, aren't much more than a micron in size, although the colonies of the organisms can be much larger. And obviously the three-dimensional stromatolites are larger, so they're very small. Again, just to reiterate the biosignatures, we have the cell components, evidence for the metabolic activity, and the physical features. So the early Earth was an anaerobic environment with what is to us today extreme conditions, but it seems that every single habitable niche had been colonized by 3.5 billion years ago. We're talking about submarine environments, sediment pools, grain surfaces, the planktonic zone, even perhaps the vadose zone. And when we can actually see cellular features, they look very similar morphologically, and they react metabolically similar to modern anaerobic prokaryotes. Therefore, the level of evolution that's been reached by 3.5 billion years ago with phototrophy is relatively high. What does that mean? What does that mean for the origin of life and the early evolution of life? Well, if we have Luca, the earliest cells here, the kinds of organisms that we're finding are far away from the origin of life. We're way beyond the origin of life, and we've got no trace of it, nothing. We don't even know. We're looking at features that cellular life that looks and acts just like modern prokaryotes, whether you want to call them prokaryotes or not, but they look and act just like modern prokaryotes. So we're far away from the origin of life. We're far away from the earliest cells. So we have no rocks that preserve this period. As I mentioned, we only have these two areas, the Pilbara and Barberton. Maybe with global warming, how can I put this politically correctly? Fortunately, unfortunately, something might appear on Antarctica. Fortunate for those who want to find it, unfortunate or fortunate for the world, but anyway. So anyway, we don't have the traces of life. So this is where I come on into the extraterrestrial life. Is there somewhere else where we might be able to find what's missing on Earth? And Hervé touched on this yesterday a little bit. So I'm going to speak mostly about Mars. And so why Mars? Well, I'll skip this because Hervé spoke about why Mars yesterday, so I can cut that out. We're speaking about early Mars. Early Mars was actually way out of the habitable zone of the planet, of the solar system, if you're looking at simply the habitable zone as a zone where liquid water is stable at the surface of the planet. If we, if we take the habitable zone today, it's just the Earth that's in the middle of the habitable zone. Venus is too hot, Mars is too cold. Go back 4 billion years. Mars is way out of the habitable zone. Venus might have been in it, and the Earth is iffy, but Mars is way out. So why do we think that Hervé showed you evidence for water on the surface of Mars yesterday. How can this be? And I suspect that Tillman possibly covered this in his talk as well. It's just that the planets were hot to begin with, and when they were cooling, although they were out of the habitable zone, they were hot, and water could be liquid at the surface. I don't know if you covered this, Tillman. Yeah, okay. So, if we look at the history of water on Mars, this is a NASA sketch. Mars, when it was consolidated, could have had water at the surface. With time, the planet cooled down quite rapidly, and conditions at the surface became inhospitable because there was no available liquid water. Although, in a punctual fashion, every now and then, an impact could possibly puncture the cryosphere, or water from the cryosphere could get up into the impact basin. So basically, if life arose on Mars, it would have been during the early period when there was sufficient water for sufficient time for life to appear. This is why we think Mars is quite a suitable candidate. Now, why is Mars a place to go for the origin of life? If life did appear, 3/4 of the planet is coated with rocks that are far older than rocks that are left on the Earth. We have the rocks on Mars that have the age of those in which life could have appeared. So this is another interest for Mars. This is another reason why, and in fact it's the reason why all the MSL and the the European Russian mission EXOMARS are going to what we call Noachian terrains, the ancient terrains, when water was present on the surface of Mars. Okay, quick comparison of habitability. I mentioned on the early Earth was, to all purposes, an ocean planet. Early Mars was never an ocean planet. Even if there was water, it was spotty. It was here, it was there. It disappeared from there, but it appeared there. But nevertheless, it had the ingredients: liquid water, carbon, nutrients, energy, and we think, we don't know exactly, but we think that hydrothermal systems were important for the origin of life. So if all these ingredients were there, we think there was life. And again, if we look at the general conditions, basic conditions, they're very similar to those on early Earth. So yes, early Mars was habitable on a microbial scale. What about ancient Mars? Now, this is what Tillman wanted to ask me about. We do have a rock. Most of the meteorites from Mars are quite young. They're about 1.2 billion years old or younger. There are a couple that are old, and one of the most notorious is this meteorite called the Annan Hills 84001. It was found in 84 because 84. It was found in 1984. It was identified as a Martian meteorite in the early 1990s. It crystallized. The rock. It's sort of the coarse part, like the coarse part of a volcanic lava, thick volcanic flow. It's a volcanic rock. It crystallized about 4.1 billion years ago, but it's shot through with fractures because the surface of Mars is has been very much influenced by impacts. So it's shot through with fractures, and in these fractures were deposited certain globules. These orange features are actually siderite. There are deposits of siderite ringed by magnesite, and the black layers between them are magnetite. Now, these are salts, and it's believed that these salts were deposited from flowing water, from water. Therefore, there was water flowing in the cracks. That's quite feasible. And there was a group from the Johnson Space Center in Houston who described, as Hervé showed, these mineralogical, in the siderite, the magnesite, they described these particular structures as fossil microbes. And I looked at them. In fact, I'll give you another anecdote about this, because this was a very strange period. We're talking about 1996, July, August 1996. The paper describing this came out in August of 1996. Well, in June 1996, I'd been studying these cherts from South Africa, and I found the first features that I thought were fossil microbes. And I'd also spent years fossilizing microbes and looking at microbes in the fossil record. It's a period that is particularly focused in my mind, because my father died in June, at the end of June. And so, you know, when something like that happens, you are psychologically very aware of everything. And in July, I went to the bioastronomy meeting on the island of Capri, and a noted French astrophysicist, Alain Léger, was there. And I was talking about the fossil bacteria, and people were very interested in my fossil bacteria. And Alain Léger said to me, you know, why don't you look for fossil bacteria in meteorites from Mars? So I wrote to the Johnson Space Center, and I'm talking about end July 1996. I wrote to the Johnson Space Center and I said, this is what I do. It would be interesting to look for fossil meteorites in fossil microbes in a meteorite from Mars. will you send me a piece, please? Well, I never got a reply. And in August, this paper came out saying, oh, look, we found life in Mars. And my first reaction was, they stole my idea, but they didn't. They got there first. Anyway, so, but I looked at these things and I thought, fossil bacteria? No, there's something wrong here. Anyway, so in early 1997, I was in Houston. I spoke to David McKay and I said to him, I'm sorry, you know, I don't believe that these are fossil bacteria. And I showed him my work and I said, you know, this is what fossil bacteria look like. In actual fact, these are the typical example of an artifact. These are just corrosion features of the minerals, the carbonate minerals. Anyway, David McKay was what we call a great scientist, because he wasn't shocked by what I said. He said to me, you seem to know what you're doing, so why don't you come and work with us? Anyway, so that's how I ended up at the Johnson Space Center. So, okay, that's a long story around an artifact. Sorry. So these structures are not fossil bacteria. The group, as Hervé mentioned yesterday, they also looked at tiny magnetite crystals and so on. But talking about artifacts and syngenicity and so on, whereas the top features are syngenetic with the rock, well, or maybe at least the carbonate is syngenetic with the rock, there was modern contamination of the meteorite. In the bottom left diagram image, you can see an image of a modern actinomycete. It's a microorganism. At the bottom right, the spotty stuff that you see on the pyroxene crystal, it was a fresh fracture surface that was left in a drawer for 2 years in Houston. These are polymers, organic polymers. Now, how did this material get onto the meteorite? Another anecdote, because these meteorites are stored in special rooms. You have to get dressed up in a bunny suit to go in to look at them. They're in cabinets filled with nitrogen. You have to use glove boxes and so on. So how on earth did modern bacteria get into the fractures of these meteorites? Well, it turned out to be quite simple, because at that period, our colleagues at the Johnson Space Center, they were very good geologists, geochemists, petrographers, etc. They were not microbiologists. And it turns out that the aeration ducts going into the chamber were filled with biofilm, microbial biofilm. So here they were thinking that everything was stored in a pristine fashion, and the microbes were saying, no, I'm coming in and colonizing and having a great time. The polymers, Houston, I lived there for 3 years, and there's a lot of petrochemical industry going on in Houston. The air is saturated with organics. It stinks sometimes. And the organics just precipitated from the air onto the mineral surfaces. Okay, modern contamination. What about ancient life on Mars? Hervé spoke to you about MSL and Curiosity yesterday, so I will concentrate on ExoMars, which is our European-Russian mission, supposed to leave in 2018, but probably will leave in 2020. These are rovers that are equipped with a huge range of instrumentation. It's actually very, very good range of instrumentation, which imitates cameras and high-resolution cameras to imitate the scientist's eyes, the hand lens, instrumentation for looking at sediment or rock texture, structure. ExoMars has instrumentation for looking at the minerals, mineral composition. ExoMars doesn't have instrumentation to look at the elemental composition, but for organic, we're looking the emphasis is on organic traces of life, because people realize that fossil microbes are likely to be far too small to be seen with an in situ mission. And also, I've shown you the kind of techniques that we use for preparing samples to have a look for microbes, so it's a bit difficult. And as Hervé said, the best thing would be to bring the samples back. So with ExoMars, we have also a mass spectrometer. In fact, we've got a laser desorption and a gas chromatograph coupled to mass spectrometer. So these are quite powerful techniques. But a very important thing about looking for organics on Mars, as Hervé mentioned yesterday, they haven't really, something's been detected, but it's really difficult because of the radiation at the surface of Mars. You've got UV radiation, you've got cosmic radiation, you've got galactic radiation. In geological timescales, I mean, we're looking for stuff that's in rocks 3.5 to 4+ billion years old. In that length of time, it gives enough, radiation can penetrate the surface. So whilst on the surface of the planet, you've got UV radiation, oxidation, and various processes oxidizing the organic matter molecules. At depth, with time, the galactic and the cosmic radiation can penetrate. And this is work from Gerhard Minnick and also Mark Sefton. They can, the estimate is that it can penetrate down to about 1.5 meters of a typical Martian regolith. This is the ExoMars drill. It's a drill that can penetrate down to 2 meters. And the idea is to be able to take a sample, hopefully containing organics, and bring it up into the laboratory for analysis. This will be a fantastic thing if it works, and let's just hope it does. But as Hervé noted, there's a big problem of perchlorates on Mars. As with the SAM instrument, the ExoMars MAMA instrument will be heating up the materials. Although now we know that there are perchlorates, and so I presume, and it's still Hervé's group that's involved with the MAMA instrument, perhaps we'll be able to bypass this problem. However, the very, very best thing will be to bring samples back from Mars because we note that it's very difficult to really, even if we manage to find organic molecules on Mars and they are suggestive that perhaps there might be life there, we will need to bring the material back to really study it in more depth. However, the very best, send a geologist to Mars. A geologist in 1 week can do what a whole mission can do, the MSL can do in one year. So I think I'll stop there, and if there are any questions, please feel free to ask.